Hello, this is a pretty quick set of slides, um, maybe one or two videos depending on how many questions I ask and how long they take for me to set into VidGrid. But we're finally going to prove a lower bound on the number of comparisons it takes in any sort of comparison-based sorting algorithm. So we're going to discuss a lower bound for running time, and there's a nice exercise for this set of slides. Okay, so here's our claim. Our claim is that the worst case lower bound on comparison-based sorting is omega, big omega of n log n. So when I say comparison-based sorting, what am I talking about? I'm talking about pretty much anything we've talked about in this class so far. So merge sort, quick sort, heap sort, insertion sort, bubble sort, any of these general purpose sorting routines. There are other types of sorting routines that are less general purpose. So there are non-comparison based sorting methods. So bucket sort, counting sort, radix sort. These are methods that look at the values, not just the relative ordering. So they might know something about the distribution of the data. So if I have randomly and uniform distributed data, it can put these things into buckets, effectively sort the buckets, and then combine the sorted buckets. If I have Gaussian data, maybe I just have more buckets in the middle and larger buckets the further out I get. And I still have an easy to sort sort of bucket size. But basically, those are algorithms that can do better than n log n, but they have assumptions about the data. And if those assumptions are broken, then those algorithms don't work very well, and in fact, a lot of them will end up n squared or worse. Not worse, but n squared at least. All right, so let's work on proving that lower bound. So consider an array of the values 1 through n. How many different orderings are there for those n values? Well, an array will have n factorial different orderings, or permutations, right? I can pick any of the n numbers for the first value, any of the n numbers for the second, n minus 1 values for the second, any of the n minus 2 values for the third, and so on. So n factorial different orderings. Let me remind you, we can only use the result of comparisons to reorder elements. This is comparison-based sorting, like merge sort, quick sort, insertion sort. Let's assume that our algorithm makes exactly k comparisons. I'm not going to figure out what k is just yet, so we'll just say we don't know what k is, but k is going to be our parameter for saying how many comparisons we have. How many distinct comparison sequences do we have if we have k comparisons? Well, this result's a little less intuitive without some more information, so let me just tell you a comparison sequence would be like if I compared the first number and the second number, and then I made some decision based off that, and then I compared the winner of that to the third number and made some decision based on that. How many distinct possible comparison sequences do we have? Well, each of them gives you a binary choice. So we're going to have 2 to the k total sequences. So for each of the k comparisons, we have a binary output. So the left is bigger or the right is bigger, and we're going to do that k times. What's a reasonable upper bound on k? Well, if we have n numbers, there's not really any reason to do more than n squared comparisons. So you might have said n log n as a reasonable upper bound because we know that we've got algorithms that work like that. But I'm going to say n squared. If you're doing more than that, you've done more than just compare every number to every other number. So n squared. What's a reasonable lower bound on k? Well, I've already told you that we can't beat n log n, so a reasonable lower bound on the number of comparisons is going to be n log n. So we don't know k, but we know that a pretty reasonable upper bound on it is n squared, and a lower bound is pretty reasonably n log n because we have some algorithms on it, and I've already told you the answer here. But what we're going to find is that you cannot do better than this lower bound. We're going to prove that. So to prove that, let me give you a couple extra tools here. So if we have 2 to the k distinct comparison sequences, for each of the k comparisons, we're basically going to return value A or value B. You could think of these comparisons as resulting in a decision tree. So let's say I have an array of the numbers A1, A2, and A3. We don't know in what order those go. But I'm going to compare A0 and A1. And depending on that, so if A0 is less than A1, I'll go to the left branch here, or I'll go to the right branch. And then the rest of this sort of shows you the entire path of getting to any of the correct sorted sequences. So let's say that A0 happens to be the smallest number, followed by A1, followed by A2. Well, A0 is less than 1, and A1 is less than 2. So I took 2 comparisons, k was 2 in that case. Well, let's say that this is the correct sequence. Well, if we start out by comparing 0 to 1, and then compare 1 to 2, and we got a no there, that means we don't know the absolute order between everything yet. We next have to compare 0 to 2, because we don't have the transitive property working for us like we did when we went down this branch. So we have to figure out if A0 is less than A2, and depending on that we go to one of these two branches, and we went to this one. So K would be 3 comparisons there. 1, 2, 3. So that's what I mean by a decision tree, to get to all the possible permutations. So this would be all the possible sequences of our inputs. So we have an n equal 3, so n factorial is equal to 3 times 2 times 1, which is equal to 6, and I have 1, 2, 3, 4, 5, 6 leaves in this decision tree. So this decision tree is going to help us figure out a couple of important details. And as a reminder here, K is going to be the maximum depth of this tree. It's the maximum possible number of comparisons we have to do to sort our input. Alright, well, of this decision tree we have here, how many leaves are there as a function of n? And in fact, actually, I'm going to start with that question on the next video, just to make sure this one doesn't get too long.